Hello everybody, this is Koren. I'm with the Shenkar College of Engineering and Design at the Department of Chemical Engineering, and I'm also the director of the Edelstein Center for the Analysis of Ancient Artifacts. We have pioneered dye analyses in Israel for the past more than a quarter of a century, and we still continue doing dye analyses and reporting on archaeological dyes and pigments, as you'll hear some of the story in my talk, which I will give today to the American Schools of Oriental Research in 2014 at San Diego. Actually, if you pay very close attention, I have a lot of slides, so please don't blink. They will go very fast. And I will, to keep you awake, I will drop a number of virtual bombshells to make sure that you're awake. And based on what I will present, I claim that the history books that have been written on this particular topic of Tyrian purple will have to be rewritten in a number of cases. The topic of my talk and the title of it is Setting the Archaeo-Chemical Record Straight Regarding Tyrian Purple Pigments and Dyes. And based on this research is based on an article that I published about a year ago. It's an archaeological chemistry, but if you're not a chemist, don't worry, you don't have to know too much chemistry about it. The title is New Chemical Insights into the Ancient Molaskan Purple Dyeing Process. And if you want to get a copy of it, just email me and I'll show you the website at the end of my talk. Now about purple snails, the topic is Tyrian purple, the purple pigment and purple dye. Let's talk about the purple snails. Where do we get them from? Well, there's a Club Med of purple snails, purple producing snails. There are three that are prevalent in the Eastern Mediterranean, and they were thousands of years ago. These are the Muricidae family of snails. They're called, according to the modern terminology, Bolinus brandaris, Hexaplex trunculus, Stramonita hemostoma, but they're commonly known as Murex snails. These are the three Club Med snails. Now, how do you collect it? Well, you have to dye for the snails. You go into the water, and we collected snails from Achziv, which is in northern Israel. Go into the water, that's my arm and that's my hand. We collected a whole bunch of trunculus snails. And now you have to extract the dye, or before the dye, the pigment. What do? You can crack the shell at a certain strategic place to expose a certain gland. It's called a hypobranchial gland, but it's a certain gland where the liquid inside this particular gland has no color at all. It is colorless. Once you cut the gland, the materials, the substances inside the gland, when they come outside to the air, they will meet oxygen in the air and also light. They will undergo photochemical oxidation, and take a look at what happens. This is spontaneously. It does it by itself. Yellow turns greenish, which turns sometimes into a blue, and finally it turns into this reddish purple pigment, the famous Tyrian purple pigment. This is spontaneous pigment formation. In the laboratory, it takes maybe up to an hour for the full color to develop. If you do it in the sunlight, it can be just a matter of a few minutes under the intense sunlight for all of this to occur. Now, how do you dye a textile with it? D-Y-E. How do you dye a textile? You put it in water, you mix it up, you can have a mixture. And now to give you an overall schematic of what goes on as far as the overall dyeing process is concerned. One of the main molecules, and don't worry about the actual structure of this particular molecule, but this pigment that you see here, this reddish purple pigment, has this molecule in there. But this molecule does not dissolve in water. To do any kind of dyeing, whether it's in ancient times, thousands of years ago, or in the industry today, for clothes of any kind, you have to take the dye, the substance that gives you color, the colorant, you must dissolve it. You can't just distribute it and disperse it into water and have colored water out of it. Each dye has to be dissolved, and on the individual molecular level, they can now penetrate into the interior of the textile fibers, and that's how dyeing is produced. So we have to take the solid pigment, which does not dissolve in water. You put it into the water, this is the molecule, And when you transform this particular purple pigment into a soluble form, and it's done by a process known as reduction. We teach reduction and oxidation in freshman chemistry, first year college level chemistry. When you reduce this particular pigment, and who does the reduction? It's the bacteria inside the gland that causes this reduction. In an alkaline solution, that is pH above 7, you get a soluble dye, and now you can put in the wool. You have the sheep over here, you shear the wool off the sheep, you comb it, you wash it, of course, you get nice white wool. You introduce it into the green solution now, because it's been reduced, it's been transformed. It now is a greenish solution. You notice that the wool inside this particular green solution is, of course, also green. But watch what happens when you pick it up in the air. When you raise it in the air, it undergoes oxidation in the air to the original purple pigment. So before we had the pigment outside of the wool, now the pigment, the molecules, are stuck. They're imprisoned inside the textile fibers, and this is very, very stable, and they will last forever, let's say. Now, in the laboratory, we one of the first to have done such natural dyeings. We were the first in Israel to do it. And you could see the green solution based on fermentation, the green solution, and then with wool in there, and then you raise the wool out after it's been sitting there for about an hour or 2 hours, and the green that becomes purple gets oxidized eventually to this beautiful purple pigment that is now caged in, imprisoned inside the textile fibers, as I said. You can do all sorts of chemistry tricks and transform it to blues and violets, which is a different story. We won't go into it in this particular talk. But you can see a plethora of purples that you can produce with this particular purple pigment. Now, the main topic of the talk are the major conclusions, the main insights. Most of the people, I dare say practically everybody, not just most, who has written about this purple pigment, and I talk about archaeologists, and I'm talking about historians, have never experimented with this purple pigment in the way they would have done thousands of years ago. Some people have experimented with the purple pigment by using synthetic reagents, synthetic reducing agents. I'm talking about experimenting with the purple pigment the same way they would have done 3,000 years ago, let's say. And once you do that, even in the laboratory, but you do it with the same tools, the same methods, the same materials as they would have done thousands of years ago, you gain some revolutionary new insights as to what is possible and what is impossible as far as the purple is concerned. Now, major conclusions. Number one, have you ever thought about the quantities of snails needed in order to dye one complete cloak from head to toe? And how much liquid is needed in a dye vat, in a vessel that is used for dyeing? Well, let's take a look at some of these Phoenician dyeing vats or potsherds from ancient dye vats from Israel. These pictures are from Israel. Tel Kabri in the up north, 7th century BCE, beautiful purple pigmented potsherd, which is, based on its curvature, belongs to a vat, a vessel, a round vessel. Tel Dor, also in north, but north central Israel, 6th century BCE, as well as Tel Shikmona. You could see remnants of purple residue on it. Tel Kisan, 11th century BCE, and here's a closer up of this purple pigment. It's 3,000-year-old object, not the person standing, but the vat itself. And you could see inside it purple pigmentation. But just because it has a purple pigment does not automatically mean that it's real purple from a snail. You must chemically analyze it. Unfortunately, some historians and archaeologists have reported that, well, they found some residue on it, and therefore it must be real purple from a snail. It will not stand in a scientific court of law. It must be chemically analyzed and then verified that it's a real purple pigment. Now, back to the original question. What quantities of snails and liquid are needed in order to produce a dyeing? Well, the vat that I just showed you, with the person looking inside the vat, can easily contain 100 liters of dye solution. for 100 liters of dye solution, and we've done dyings, natural dyings in the laboratory, not 100 liters of it, but small scale experiments. And since I'm in the Department of Chemical Engineering, what chemical engineers do is they do scale up from laboratory size to large industrial size. When you scale up, you could see that you could dye with 100 liters of solution, you can dye 1 kilogram of wool, which is about one cloak, one complete cloak would be wool that will be twisted, spun into threads and then woven into one cloak. Now, the number of trunculus snails that are therefore needed in this 100-liter dye solution to dye 1 kilogram of wool. Does anybody have any idea of how many snails it would take? Well, here's the answer. It would take a total of 10,000 snails in order to dye 1 cloak for His Royal Highness. And the ratio that I came up with, which is a very nice ratio, I call it 1:10:100. The 1:10:100 ratio is that for every 1 gram of wool, you need 10 snails in 100 milliliters of dye solution. Now, this ratio of 10,000 snails for 1 kilogram of cloak, if His Royal Highness did not have so many slaves to gather all of these snails, he could have done dyings with 5,000 or even 8,000 snails. But if you want to get a nice purple color, a deep reddish purple, or what I call in-your-face purple, you need 10,000 snails, and then everybody will look at you, the Royal Highness, when you walk out with this royal cloak and say, wow, that's royalty. Now, the second major conclusion that we came up with is the provenance studies. Provenance studies, zoological source of purple dyings, archaeological purple dyings. In archaeology, in archaeological science, you've heard many times in these meetings where they analyze a clay vessel, for example, and based on the elements that are in this clay vessel, and they do analyses based on neutron activation analysis, X-ray fluorescence, ICP, atomic absorption, all sorts of methods that give you elemental analyses of certain clay fragments. And then geographically, you could also analyze different earths from different parts of the world. And you can say, this clay vessel came from this part of the world. That's called provenance studies if you have the chemical composition of the object. Well, what I do is also provenance studies, but malacological or molluscan provenance studies in order to identify not the geographic source of the dyeing, of course, but the zoological source of the dyeing. And we do that by various methods, but the main method is chromatography, high-performance liquid chromatography or ultra-performance liquid chromatography. And without going into the details, simply stated, chromatography gives you a separation of components that are in a mixture. For example, if you take a look at this particular purple pigment that has come out of this snail, we have found that there are about 10 different components. Some of them are yellow, some of them are blues and reds, some of them are more reddish purple. And a chromatogram is a graph of the result, and each peak that you see here is a separate component. So that if we analyze any pigment, we see this particular pattern, each peak, we know what components are there. There are about 10 different components there. And just like you want to identify a person, yes, you can identify a person with one fingerprint, but it's best if you have 10 fingerprints. This is chemical or chromatographic fingerprinting that based on the substances and the dyes found in this pigment, you can identify what it is. You can do quantitative analyses, as we've done multi-component analyses on archaeological samples and also modern samples. And this is just to give you an idea without going into the details. You could do a quantitative analysis. This is normalized to 100%. And these are actual peak areas, but you can think of it as quantities of the yellow components and of the blue indigoid components, and if there are any violet components, and as well as reddish components. You could see simply by the graph as it's growing, by knowing not just what substances are in the sample, but how much of the substances are in the sample. This is qualitative and quantitative analysis. You can get a very good chemical fingerprinting of this particular pigment. But of all of the 10 dyes that I just showed you, there are 3 main components, 3 main dyes in this particular purple pigment. Those are the most important. And they're called the Indigoids. And I published on it in 2006. And the 3 main indigoids, and I'm showing you right now the molecular skeleton of an indigoid based on indigo. You have indigo in there, which is a blue color. You also have monobromo indigo. As the name implies, it's indigo skeleton with only 1 bromine atom. And you also have dibromo indigo, which is indigo skeleton with 2 bromine atoms, as you can see on the molecular skeleton here. The color of indigo, as we know, of course, is blue or blue-violet. Monobromo and dibromo indigo is reddish-purple. Monobromo indigo is actually a color in between, something like violet, as the slide indicates to you. Now, another thing that people do not understand about the particular purple snails is that not all snails were created equal. It's not a democratic society among snails, what can I tell you? Not all snails were created equal. And there is a difference between these snails. All snails, such as Brandaris, Hemostoma, and the others, have mainly dibromo indigo, the reddish-purple pigment in there. Of course, they have some other trace amounts of others, but that's the main component. This is what we published in 2008. The trunculus snail is radically different because it has all 3 of the indigoids, but especially important to look at the monobromo indigo, and only the trunculus has significant quantities of monobromo indigo, MBI. In addition, people do not understand that there are 2 subspecies or chromatic varieties of trunculus snails themselves. There are trunculus snails that will give you much more indigo than dibromo indigo. Since there's more indigo, it's called an indigo-rich trunculus, and it will give you bluer dyings. On the other hand, there's also trunculus snails which are rich in dibromo indigo, more than indigo. They're dibromo indigo-rich trunculus snails, and they'll give you reddish-purple dyings. So that if you find a monobromo indigo in a modern pigment or an archaeological pigment, since only the trunculus has much monobromo indigo, the finding of monobromo indigo in the pigment tells you automatically that a trunculus snail was used. Furthermore, to date, all archaeological purple pigments that were analyzed from sea snail and molluscan sources, all archaeological purple pigments and dyes that have been analyzed properly, specifically via HPLC, have detected significant levels of monobromo indigo. This is not just the analyses that I've done. I've also looked in the literature, analyses that were properly performed. Some analyses were not properly performed. Analyses that were properly performed by HPLC on archaeological samples, every single one that has been analyzed has shown significant levels of monobromo indigo, which means automatically that all archaeological molluscan purple pigments and dyes were produced from the trunculus species. And if you wanted to get a red-purple dyeing, you use a dibromo indigo-rich trunculus. If you wanted to get bluer dyings, blue-purple or perhaps violet dyings, you use an indigo-rich trunculus. And ancient peoples knew from which kind of trunculus to obtain, where to get it, where to collect it, which trunculus to use. To give you some examples quickly, one purple pigment that I analyzed from a King Darius I, or King Darius the Great marble jar, which had residual purple pigment. When I analyzed it, I saw that it has a significant amount of monobromo indigo, as well as some of the others, which means it can only come from a trunculus snail. This was used in Persia, or it was dyed in one of the areas that was controlled by ancient Persia. King Darius in ancient Farsi is Daryavahush. That was a purple pigment. And also a Herodian cloak belonging to King Herrod. This is a fragment that was found up on top of Masada. You have the substance composition. There was some indigo, a lot of monobromo indigo, and a lot of dibromo indigo, as you can see over here. But once again, it's a reddish purple dyeing, and it contains a lot of monobromo indigo. This is probably the biblical argaman, but that's a different lecture. And finally, to give you another example of a more modern, quote, quote, textile, a late Roman period textile, that's an Egyptian textile from in Katon Nasi in Antwerp, a nice museum of Coptic and other Egyptian Roman period textiles that we published on. A beautiful polychromic textile, beautiful colors. In it, when we did microscopic analyses, we can see visually that there are 3 different colors in there. There's a blue-purple color, there's a red-purple color, and there's another yarn which was red-purple, but even redder than the one before. In all of them, we found monobromo indigo. In all of them, the trunculus snail was therefore used. In the top picture that you see, to get red-purple, as I said before, it was a dibromo indigo-rich trunculus. To get the blue-purple, you take an indigo-rich trunculus. Now, how did they get, in the bottom picture, a red-purple that you can see even visually is much redder than the one up above? And it still had monobromo indigo. The answer is simple. Trunculus was used, but also Brandaris or Hemostoma, which give you only dibromo indigo, were added to top off and to give you even a redder color. So, what about the Brandaris and Hemostoma? As I just said, the Brandaris and Hemostoma snails were not used alone, could not have been used alone, no matter what the history books state about using Brandaris for Tyrian purple or royal purple, imperial purple. And the reasons are chemical reasons and other logistic reasons. First of all, as we said, monobromo indigo was found in all archaeological samples. If they were going to use Brandaris and Hemostoma alone, first of all, we wouldn't have found monobromo indigo. But besides that, the dye vat would have needed many more than 10,000 snails, since the quantity of pigment in a Brandaris or Hemostoma is even much less than a trunculus. Even the trunculus, to use 10,000 snails, is an astronomical amount. To use Brandaris and Hemostoma, you need tens of thousands, which doesn't make sense. Besides that, if you want to get red-purple dyings, you can use a trunculus anyway to get red-purple dyings, because you could use, as I said before, the dibromo indigo-rich trunculus will give you the red dyings. And therefore, so what's the role of Brandaris and Hemostoma? As I've said before, the Brandaris and Hemostoma were used with dibromo indigo-rich trunculus for topping the dye to produce even a redder color, but not by themselves. This is all based on current archaeological and chemical evidence. As I said, to date, if tomorrow somebody finds a different sample, okay, then we can incorporate that into our analyses also. But the last and important aspect of the purple pigment is there's a controversy as to who discovered the purple pigment. Which people discovered it? Now, this is a big misunderstanding among historians and archaeologists, where they use the words pigment and dye synonymously. Pigment and dye are different aspects of the word colorants. As far as hierarchy is concerned, there are colorants. Some of them are pigments and some of them are dyes. Now, what's the difference between a pigment and a dye? A pigment is a water-insoluble colorant. It does not dissolve in water. It is used for painting, for example. A dye is a water-soluble colorant, which is used for textile dyeing. Now, A pigment, yes, can be transformed, converted to a dye, like indigo or the dibromo indigo or the purple pigment is solubilized by transforming it, reducing it to a dye. A dye can also be transformed into an insoluble, water-insoluble pigment. But you have to keep the two separate. Now, as far as the archaeological and chemical evidence is concerned, there is use of purple as a paint pigment from the Aegean, which dates from about 17th century BCE and perhaps even before. Many of you are familiar with the famous fresco in Akrotiri in the Aegean island of Santorini or Terra in 1700 BCE, thereabout, for the saffron gatherers. And this beautiful wall painting, what was detected in the saffron of the on this wall painting, some use of real purple. This was done by Greek colleagues of mine, and they detected purple pigment in the crocus, in the saffron of this particular image, in this particular wall painting. Now, what that tells us so far is, okay, we have evidence that in the Aegean, they used the purple as a pigment for painting. To date, there have not been any findings of purple pigmented potsherds from dye vats that predate or are even contemporaneous with those of Phoenician potsherds with purple residues. There is no purple pigmented clay fragment that was found in the Aegean that you can state that it's part of a purple dye vat. But as far as the Phoenicians and in the Levant are concerned, there's archaeological and chemical evidence on the use of purple as a textile dye from the 13th century and probably even before, such as the pictures that I showed you before from Tel Kisan in Israel, 11th century BC, northern Israel. And you could see on these rounded fragments, and you could see purple residue, which I've analyzed also, and they're real purple, such as also Tel Kabri, beautiful purple residue on this clay fragment, this potsherd, which, based on its curvature, belonged to a dye vat for the dyeing of textiles. So that in the Levant, the Phoenicians have a record of using textile dyeing. So that to date, and again, as I state, the current archaeological and chemical evidence is that, yes, the Minoans and the Aegean people discovered the purple pigment, let's say about 4,000 years ago. But there's no evidence that they used it before the Phoenicians as a purple dye. The Levantine Phoenicians chemically were able to transform that particular pigment to a dye, and were the first to use it for textile dyeing a few centuries later. So the conclusions are of my talk, the conclusions are as such. Number one big vat for 100-liter solution can dye 1 kilogram of wool, needed 10,000 trunculus snails. All archaeological purple dyes and pigments produced from sea snails were produced from trunculus snails because of the evidence of monobromo indigo. You can get with trunculus red purple with dibromo indigo rich trunculus, and you can get blue purple with indigo rich trunculus. What about the Brandaris and Hemostoma? They were not used alone, but they were used as needed as additions to trunculus in order to give you redder dyings. And who discovered the purple? Well, the people of the Aegean discovered the purple pigment for painting, let's say about 4,000 years ago. But the Levantine people, the Phoenicians, discovered the purple dye for textile dyeing about half a millennium later. That's all, folks. Thank you very much for listening. If you have any questions, you can see the website on the bottom of my last slide, edelsteincenter.wordpress.com. You can look into it, and if you have any questions, you can write me an email. Thank you very much.